Have you ever stopped to think about how an idea in your head actually becomes a working app on your screen? I mean, it's a wild journey, right? From a human thought into the secret language of machines, a world that's really just made up of ones and zeros. Well, today, we're going to pull back the curtain and demystify that whole process. We're going to get to the bottom of the magic behind the code.
So it all starts with this one simple but kinda deep question. We know computers only get one thing, a constant stream of ones and zeros, machine language. So why on earth do we have thousands of different programming languages? Python, Java, JavaScript, C++, the list goes on and on. Why do we have all this extra complexity? Well, that is the central mystery we are setting out to solve today.
The short answer? Well, programming just isn't a one-size-fits-all kind of deal. You see, different problems demand really different solutions. And so, different languages have been designed over the years to be amazing at very specific jobs, or what we in the field call domains.
I want you to think of it like a mechanic's toolbox, okay? You wouldn't use a giant sledgehammer when you really need a tiny screwdriver, right? It's exactly the same for programmers. If you're doing super intense scientific calculations, you're probably going to reach for a language like Fortran. Need to generate complex business reports with perfect decimal points? The classic choice for decades was COBOL. Trying to build an AI that can actually reason about things? You'll need a language like Lisp, which is just fantastic at manipulating symbols. And if you're building the very foundation, something that talks directly to the computer hardware like an operating system, then you need the raw power and speed of a language like C.
So you might be asking, why should I care about all these different languages? Here's the thing. Understanding the ideas behind them is way more important than just memorizing the rules of any single one. It trains your brain to think more logically, it helps you pick the right tool for whatever job you're facing, and honestly, it makes learning the next big language that comes along so much easier, because you'll already get the core principles.
And all of this leads to an even bigger question. With all these choices out there, what actually makes a programming language good? Is it just what people prefer, or are there some concrete, objective things we can use to judge them? Well, it turns out there are pretty much four main ways we can evaluate any language. First up is readability. Just how easy is it to look at the code and understand what it's doing? Can someone else, or let's be real, you 6 months from now, figure it out? Next is writability. How easily can you take an idea from your head and turn it into code? Then we've got reliability. Does the program do what it's supposed to do every single time without weird bugs? And finally, there's cost. And that's not just about money. It's also about the time it takes to train people and keep the software running smoothly.
Now here's where it gets really interesting. Two of the most important things on that list, readability and writability, are often fighting each other. Yep, they're in direct conflict. A language that lets you write code super fast and in just a few lines might be almost impossible for another person to read and understand. This is a fundamental battle at the heart of designing any language.
And here is the perfect, almost unbelievable example of what I'm talking about. This is real code written in a language called APL. For the person who wrote this, it has incredible writability. They can express hugely complex mathematical ideas with just a handful of symbols. But for the rest of us, the readability is basically zero. I mean, it looks like ancient hieroglyphs, right? This is that trade-off taken to its most extreme.
So, to help us navigate this huge and sometimes confusing world, it helps to group languages into what we can think of as families. Each family shares a core philosophy, a fundamental way of thinking about how to solve problems. Let's take a quick look at the main ones. Okay, the biggest family by far is imperative. This is how most people think about coding. It's basically like a recipe. You give the computer a list of step-by-step commands to follow. Then you've got functional programming, which treats everything like a math function. It just transforms inputs into outputs, nice and clean. Logic programming is totally different. You give it a bunch of facts and rules, and the computer acts like a detective, figuring out the answer for you. And finally, there's object-oriented programming, which is used in languages like Java, where you bundle up data and the things you can do with it into these neat, reusable packages called objects.
All right, so if we know what makes a language good, and we know about all these different approaches, why hasn't someone just built the one perfect language that does everything? The truth is, they can't, because every single choice a language designer makes is a trade-off. Just take the classic battle between reliability and cost. And by cost, I mean speed. A language like Java is built for safety. Before it does anything, it double-checks and triple-checks to make sure the operation is safe. This makes it super reliable, but all that checking slows things down. C, on the other hand, is built for one thing, pure, raw speed. It trusts the programmer completely. It does zero safety checks, which makes it lightning fast,
but it also means one tiny mistake can bring the whole system crashing down. Safety or speed? That's the designer's dilemma. Okay, for the final piece of the puzzle, let's look at the actual magic that happens under the hood. How does the code that we write in any of these languages actually get understood and executed by the physical hardware of a computer?
So this right here is the basic blueprint for almost every computer you've ever used. It's called the von Neumann architecture. And its key idea is actually pretty simple, but it changed everything. The program's instructions and the data that those instructions use are stored together in the same memory. This design is the big reason why those step-by-step recipe-like imperative languages became so popular. They perfectly match the way the hardware works.
And at the very heart of it all is this simple, relentless loop. The fetch-execute cycle. The computer's brain, the CPU, fetches an instruction, figures out what it means, does it, and then moves on to the next one. Over and over and over again. Billions of times every second. This exact cycle is happening right now on the device you're using to watch. So how do we bridge that final gap between our human-friendly code and those raw machine instructions? Well, there are two main ways. On the left, you've got the compiler. Think of it like a master translator who takes an entire book from English and translates the whole thing into French before you even read the first page. It turns your entire program into machine code all at once. Then, on the right, you have the interpreter. This is more like a live simultaneous translator at the UN. It reads one line of your code, translates it, runs it, and then moves on to the very next line. But what if you could kind of get the best of both worlds? That's the brilliant idea behind a hybrid approach, which is what Java is famous for. Your Java code gets compiled first, but not into machine code for one specific computer. No, it's compiled into this universal middle ground language called bytecode. Then, this bytecode can be run on any machine on the planet that has a Java Virtual Machine, or JVM, installed. The JVM acts as that final interpreter, giving Java its legendary write once, run anywhere superpower.
So, after all that, what are the big ideas you should walk away with? First, having so many languages isn't a bug, it's a feature. We need a whole toolbox for a whole world of different problems. Second, there is no single best language. There are only trade-offs. Every language is a collection of choices between things like readability, speed, and safety. And finally, the real magic that connects our human ideas to the silicon brain of the computer is the hard work of compilers and interpreters, tirelessly translating our thoughts into pure action. And that leaves us with one last, really exciting question to think about. For the last 70 years, the way we build programming languages has been shaped by the architecture of our computers. But that architecture is starting to change, with things like quantum computing and massive AI systems on the horizon. The old rules might not apply anymore. So, what will the next great programming language, one designed for a totally new kind of machine, what will that even look like? That's something to chew on. Thanks for joining me on this explainer.